Good morning, everyone. Let's get started. This is a panel on the future of HPC. I'm your moderator, John Cazes. I'll just give a little bit of background about myself. I've been doing something related to HPC since the early 90s. My background's in astrophysics. I've programmed on all sorts of systems. In the last sort of 15, 20 years, I've moved more into just HPC support rather than research, scientific research. And I have some strong opinions on the future of HPC, but I'm going to let my panel express their opinions. And so now I'm going to let the panel introduce themselves. And after we're done with the introduction, we'll get a little bit of overview of HPC and where it's come from and where it is now from our elder statesman, John Towns. And then we'll do a little audience survey. And then we'll get started on our discussion, okay? So Dennis, you're first.
Okay, yeah, can you hear me? Okay, very good. So my name's Dennis. I'm sure I've met some of you the past few days. I'm a permanent researcher in Willsch, in the Willsch Supercomputing Center, and I'm also a lecturer at the University of Applied Sciences in Aachen. And my main work is in the unique quantum user facility, where we provide access to several of these new quantum computing devices over here. And even though this looks all sort of flashy, right? So I'm not like the average quantum hype guy. And as an example, I've highlighted a few statements from papers of mine. So one was in 2017 here. That was just when the IBM quantum experience came out. So, the first publicly available quantum computer, or proclaimed to be a quantum computer, with 5 qubits. And then we tested this extensively, and we found this is actually not a computer. So it doesn't even satisfy the necessary criteria for a computing device. And of course, we published this, as you do, with honest scientific results, right? Then another example is in 2020. There was a lot of negative vibes against the D-Wave quantum annealer, mainly from the Universal Quantum Computing, from the theory group. And then we actually tested this device as a black box kind of thing, and we actually found it's not so bad. And it's actually performing better than QAOA on an ideal quantum computer simulator. And we actually also published that, went through. Then in 2023, we used 2048 GPUs in an HPC simulation of a quantum computer algorithm, of Shor's factoring algorithm. And then we posed the challenge of factoring on any real quantum computing device a number that is larger than what we can factor by simulating Shor's algorithm on 2048 GPUs. And when that's going to happen, I don't know, but not anytime soon. And the last example is that just this year we published that the superconducting quantum processors, which is one of the most promising technologies, that these actually face a very fundamental physical challenge. And we got this published in Nature Physics, so whatever that means. But this is the sort of statements that you can expect from me in this panel.
How did you get this in the right order? I don't know. We sat down randomly. How did you get the slides?
I'm prescient. I don't know.
It's amazing.
Actually, yes.
Somebody's prescient. Yeah. Hi, folks. I've met several of you this week, and it's been a great week, by the way. I've really had a lot of fun doing this all with you. I'm not used to being called elder statesman. I don't think I have enough gray hair quite yet, but okay, on this panel, fine. So I've been doing this stuff since about 1989 or so. So I've seen a lot of technologies come and go. I'll do the little bit of intro when we get there. But I've had a lot of different positions over time, and I like to, and particularly for this context, I like to consider myself as being relatively successful in my career. But it was a series of failures that got me here. So I was a failed general relativity physicist. I became a computational scientist, which was bridging between the physics and computer science back in the early 90s, in which that term computational scientist hadn't even been coined yet. So I was doing these numerical simulations of black holes, spacetimes. I'm a failed network applications guy, although there is a slight success story that came out of that. For if anybody is familiar with the iPerf network testing tool, have you ever heard of that? test end-to-end performance and reliability. That tool was actually developed by my team back in the early 2000s and has now become sort of a standard tool in a network engineer's toolbox. So what I ended up becoming is a research infrastructure builder and a builder of a number of things, and not just physical systems, supercomputers. I've built 3 or 4 top 500, top 10 in the top 500 systems, but I also build research organizations like the Exceed project, which I think was fabulously successful for 11 years. I'm one of the PIs on the Access environment in the US at this point. I'm also the deputy director at NCSA. Another thing to keep in mind is I've seen this from the bottom and from the top. So when I started at NCSA in the late 80s, I was a graduate student. So I've gone everywhere from a graduate student to the deputy director at NCSA. So I've sort of seen it all from that perspective as well. So hopefully I can provide some of those perspectives in our discussion.
Thanks.
I have my own. Okay, so I'm Estella. I'm very glad to be here, and well, that's also me a little bit in a nutshell. If you go like through my CV with the bullets that you typically put there. So I would start maybe from the bottom, because that's the oldest stuff. So I have a master in astrophysics from the Complutense University in Spain. And then I worked for a while before starting my PhD as an astrophysicist in Switzerland, to then continue with a PhD in astroparticle physics, or formally in physics, at the University of Geneva. So what I was doing there was simulating a detector, an X-ray polarization detector. So I realized I spent most of my time programming, less of my time really doing physics, and actually I enjoyed more the former than the latter. So I moved more towards the computer science part of things. So I moved into the Willsch Supercomputing Center in 2010, where then recently, since 2 years ago, I'm leading a division together with a colleague that is called Novel System Architectures. So what I do there, or what we do there, is to look into how should we try to build next generation of computers in a more energy efficient manner, and in general more useful for the application developers that have very diverse requirements. So it's about system architecture, about putting heterogeneous resources, CPUs, GPUs, other kinds of accelerators, even quantum computers into our HPC infrastructure. And we do a lot of these things in large collaborative projects, European projects, most of them, where we do from hardware prototyping, system software development to run those systems, then application testing and porting on these platforms. So it's quite interesting because it's a little bit like the whole wideness of HPC into a small research project, which gives a very wide view of what is out there. Yeah, and then at the same time, I'm also a professor at the University of Bonn. So I do teach then on the master's degrees, introduction to high performance computing. So it's kind of a tandem position between a research center and this academic position from university. Yeah, so I hope that here on the panel I can share a little bit of what we're seeing through all this prototyping and playing with wide, interesting systems. So my picture there is in front of one of our earliest prototypes, where we build what we call the booster, so a system, a cluster made only of accelerators, made of the Intel Xeon Phi Knights Corner at that time, that were designed as accelerators, but we took the whole stuff to it and operated in a bit weird manner. Okay, that's it.
Thank you.
And hello everyone, my name is Maciej, and I'm from POSI Supercomputing Center. I usually don't look like this in nature, as you can see. And that's a photo of a quokka, by the way, as well. So yeah, I originally come from Warsaw, from Poland, where I was studying mathematics. So my background is mathematics. My master was in mathematics. And then after finishing studies, I actually applied for an internship in a supercomputing center, a local supercomputing center at the University of Warsaw. And at that time, I didn't know anything about Linux, actually. So in first 2 weeks, they gave us like a very comprehensive training on Linux, C, C++, Fortran. And then we also received a training from a person from Cray that came to Warsaw to teach us how to optimize codes on a supercomputer. And then the next 2 months, my task was to accelerate an application on a Cray system. So it was quite interesting. I was sitting there in front of the computer trying to change the code, and all of a sudden it turned out that I was able to vectorize one loop, and I got a job. So then I started to work in a supercomputing center as a supercomputing application specialist. We're basically supporting researchers to optimize their code on a supercomputers, and I just love to do it until today. Now I lead a group at Posey Supercomputing Center that does that for Australian researchers. On the way, I also did a PhD, which was in a computational science, looking at mathematical modeling and biology. I actually so one of my colleagues had a discussion session here about finishing PhD. I actually had 3 different PhD projects, so I could speak about, how to recover after failing a PhD, which I hope won't happen to you. But I finally finalized my PhD after kind of like 10 years, I think, because it was done after hours when I was doing also the supercomputing application specialist job. Yes, I think that's me in a nutshell.
Thanks. Okay, John, you want to talk about HPC in general and how we got where we are today and how it's changed?
How we got where we are today. Well, I think sort of an overarching statement I want to include in this is that in the 35 plus years of my involvement in the HPC space, many technologies have come and gone, although a lot of them don't go, as it turns out. The ones that go generally don't actually show up too well, meaning that they aren't terribly successful or widely adopted in the community, and they sort of fade away. But many technologies have lasted for a very long time. So when I started, we didn't have microprocessor-based systems. A GPU hadn't been invented yet, and we were working on more specialized processors. And in fact, in many ways, the 2020s are looking a lot more like the 1980s than you might think. There were a lot of different systems out there from different vendors. They had different types of processors that were custom built by them. And it was really the rise of the desktop PC that took over things, and the microprocessor became a commodity and much cheaper. So in the early 90s, we saw the emergence of clusters, initially as more as high throughput engines, but as parallel systems by the late 90s. And it wasn't until the early 2000s, I think it was 2001 or 2002, that IBM had its first product that was a cluster. It was actually based on a design of a system we had done together with them at NCSA in the very end of the 90s and the beginning of the 2000s. It was kind of funny to see that come out because the standard configuration that they would provide was exactly the configuration that we had in NCSA. So they were just buying another one at what we had finally built. So the microprocessors became the sort of dominant technology that the systems were based on. But even they evolved quite a bit. So when we first had microprocessors being used, they were single core. I don't know if anyone's ever seen a single core CPU in this room. And it wasn't until later that a number of basically physics limitations on device feature size and clock rate forced the slowdown in the increase in the clock rate of the microprocessors. So for a variety of reasons related to something called Dennard scaling and also Moore's law, which are related to one another but somewhat different, essentially what we've seen in the last 20 plus years has been not increasing clock speeds, but more and more cores, or as happened in the sort of mid-2000s, the introduction of other technologies like GPUs. And so what we're seeing now in the 2020s is the emergence of a number of different types of processing capabilities. So microprocessors are still out there, but it's the only way to get more out of them is to add more cores and make them bigger, and a few engineering tricks to try and get the clock rate up a little bit. But unfortunately, the power leakage is too much, and thus you can get a lot of heat dissipation and other things. I don't want to go into microprocessor design here because that's not what we're about. But there are physical limitations that drive that, as I said before. But we're seeing these other architectures emerge, right? So we've mentioned quantum computing, but there are a number of other things out there, particularly in the AI space right now. There are a number of vendors that are trying to produce novel platforms to specifically support AI and ML. So we see things like GraphCore and Samanova and Cerebrus. These are companies that are producing these specialized platforms for AI applications. So I think the other thing to keep in mind is that as new technologies do emerge, if they are wildly successful in the community and in support of applications, they tend to get more closely integrated to the processor itself. So I'll use the GPU as an example. 25 years ago, 20 years ago even, there were no GPU-based systems out there. And we were just beginning to explore the use of GPUs as computational engines at NCSA in those days in collaboration with NVIDIA, as it turns out. By the late 2000s, there were systems coming out that had large numbers of GPUs in them. We had one of those at NCSA called Blue Waters. It was a very successful machine. It had 4,000 GPUs in it. These were K40s and K80s for those that remember the history of these things. But the point is that in that case, the GPUs were quite successful, but they were connected through an interface. It was very slow to communicate back and forth to the GPU. You still see that problem today because they're still on these interface cards. But what you'll see in future microprocessor designs is you'll start seeing those GPUs integrated into the CPU itself. And as other technologies are more successful, that will happen with them as well. That's just a natural technology path because it allows you to take advantage of what the CPU itself provides. And we will still need those for various things going forward. But these newer technologies allow us to accelerate things in different ways. Will get incorporated, and we'll need a number of them because they tend to solve a somewhat narrow set of problems. The whole GPU thing was quite largely by happenstance that while they came out of the gaming industry and we discovered that they were really useful for scientific applications, there was no anticipation that they would be so effective for AI and ML. And that happenstance has made NVIDIA now the most profitable company on the planet, or close to it.
First or second, can't remember.
Incredible to see this company that we saw as a small company 20 years ago now be where it's at. It's been an incredible transformation. So this gets to some of the questions that were in Slido if you looked over them about how technology evolves. And I guess another point about that is the sorts of technologies that survive long term provide benefits across a range of applications, right? So you've done a lot of training in MPI, and what I remember 30 years ago was MPI hadn't been formed as a standard as yet. We had a variety of message passing capabilities. I guess it was just at about 30 years ago that the standard first came out. 94, 95, something like that.
Mid-90s. I didn't use it until probably 2000s.
Yeah, I can't remember when it exactly came out, but I was using things like PVM. Nobody's heard of that. Well, okay. There is another elder statesman here, so there are a few others. So there are a few others that have seen some of these technologies, but the reason that MPI became so successful long term is that you could use it on everything, right? It gave you a least common denominator that was useful across all the different architectures, and they were very different. And so technologies that have that ability to be useful in broad sense are going to survive long term. We've seen a lot of technologies that are only successful in narrow ways, either domains or types of applications, and they tend not to survive long term. Although there are a few people that don't want to let go of them sometimes. So we've seen some of these things come and go, some of them come and stay. You'll see the mix of that, and you can't really predict it so easily, other than to recognize there's some characteristics of these technologies that increase their probability of long-term sustenance or long-term success in the community. So that brings us, I guess, to today.
The survey.
With now another growing variety of technologies that are coming up, which makes it exciting, actually, right now.
Yeah. So I want to start this with, okay, hold on. Little audience participation. So first, before we get started, we're going to have a discussion up here, but I encourage you to be part of the discussion. If you have a specific question or comment you want to make, you can go to a microphone. And we're going to start with what we have in Slido, but first we have a little survey because I want to talk about these technologies. So the first one, okay, languages. We're starting with Fortran. Fortran, yes. Great. It still lives. It's been predicted to die for years and years and years, but it's great. Okay. C, C++. I'm going to put them together. Yeah, okay. Sorry. C, C++. Can't hit it. Yes, lots and lots of users. Okay. We get a lot of questions about Rust and Julia at my center. I know there's at least one of you using Julia. 2, 3, 4, 5. I've got a quick question for you. Have you ever used it outside one node? It works across nodes. Okay. Maybe we'll look into it and install it if it's performant. And Rust, any Rust users? Okay, I haven't heard about that one in a while. It was the hot thing about 3 years ago. MATLAB. I'm sure there's people in here who use MATLAB. Wow, fewer than I would have expected. Okay, now let's move on to something more specialized. CUDA. How many CUDA programmers are there? How many CUDA programmers are there in here before this? Okay. And OpenMP? MPI? Yeah. And OpenMP and MPI are the mainstays, right? They're everywhere. OpenACC. HIP. Any AMD love? Oh, a little bit. I have it on, what I've heard is, yeah, if you're doing CUDA, you can do some HIP. If you're doing HIP, you can do some CUDA. So, oh, you know what? We left off SYCL. Any SYCL users, one API? Oh, okay. I bet you're C++ mavens too. Is there anything in here I didn't cover that you think is important for HPC? Python. Oh, I can't believe we left off Python. You made the list, Elsa. Okay, other than Python, abstractions, it's a little more specialized. You want to say Akka, right? Okay. So there are frameworks that greatly help you in parallelization. So there are tools out here other than the basic ones, but I personally think it's really important to understand the basic ones. Understand some MPI and OpenMP, whether or not you use it. Understand some CUDA, even if you don't use a GPU. It helps your understanding of how the hardware works. Oh, there's a good one. No, you should not. Yes. Okay, so resources. How many of you run on large scale? And by large scale, I'm going to say a cluster with more than 500 nodes. Oh, a good bit. That's great. How many of you just run on small scale, like local departmental clusters? And does that mostly meet your needs, or is it that's just what you have available, so that's where you're stuck? Okay. Well, that's good. And those small-scale clusters are incredibly important, right? Because that's how you learn, that's how you get trained, and it helps you move up and out. And I don't think they get funded enough either. Okay, cloud. Who's running HPC in the cloud? Anybody? A few? Do you run there and on sort of regular centers? And if you do, is it much more difficult in the cloud? So on-demand helps, but you have to pay. How many of you do scientific work just on your laptop? I don't mean just data analysis, but some sort of simulation. Oh, okay. I'm impressed because laptops are pretty powerful now. It's a resource you should use. Am I missing anything for where you run? Is there some area other than centers in the cloud? Specialized systems? Does anybody run on specialized hardware for machine learning or anything? I see one hand. What do you run on? Oh, wow, yeah. Congratulations. Yeah, and I hope it works really well for you. It's a very impressive technology. So, like John alluded to earlier, in the 80s, early 90s, HPC was all over the map in hardware. There's a lot of specialized hardware. And then it all kind of disappeared with commodity parts. And now it's coming back because of all of the special purpose hardware built for machine learning. And it's partly maybe going to be our job to figure out how we can utilize that. But we're going to get there. But first, this is where we have our discussion. And so the questions are in Slido. And right now, the top question, I assume it's still there, is about quantum computing. Okay? So I don't want this to totally dominate, so we're going to talk about it for a little while, but we could talk about it for hours. So let's start with quantum computing, and I'm going to rephrase the question a little bit. Is all of HPC going to be quantum computing? Am I going to have to learn how this works? I'm looking at our current expert, and then we'll move down because everybody knows a little something about it. Go ahead, Dennis.
Okay, yeah. So the short answer to the question is no. The long answer is there's two sides to the coin. So one is, and I'm gonna talk of the positive side first. Quantum computing is certainly a very interesting technology. So I do encourage everybody to. I mean, these systems are available online publicly, right, for anybody, at least the smaller systems. So if you think it's interesting for you, and only then, you can just try it out and see what it can do, because it's an interesting computation model. Otherwise, I wouldn't be doing it for 10 years if I weren't convinced of this. However, it's one of the, say, youngest new technologies out there. It certainly has a lot of hype behind itself, and certainly also unjustified in a sense, which is a bit unfortunate. But, so the question was, yeah, do I need to worry about it? If it's really like this, say, the next big thing, the disruptive kind of technology that if you don't look at it right now, that it's a mistake and tomorrow you'll be left out. If it was really like that, then, I mean, we haven't seen any of this in the past, right? Rather, the community of users needs to adapt to new technology. It needs a broad user base. It needs to be able to run and support a lot of applications, as John just introduced. And if it's really coming to that for quantum computing, then this will take time. And if it's relevant for your particular field of work, you will have enough time to adapt, and it will naturally come to you. So if you don't find it interesting, there is no need to worry about it just yet and just to force it into your brain, so to say. But then it will come over time if it's relevant. And if not, then it's not relevant. Like, there has been a lot of technologies. John has also listed some. FPGAs is also one. They do have few applications. They still exist. And if it's relevant for your particular field, you will be exposed to them. But for the broad majority, it's not important. And it's really very hard. It's impossible to predict where quantum computing will end up. It can be both extremes. It can either be it will totally vanish. This becomes less likely because of the hype at the moment, but it can totally vanish. Can also be very important for a broad class of applications if the devices eventually really can deliver what the theoretical models would have us believe. And this is still a big question. It's interesting to watch this, but okay, yeah, say it again. The answer to will I need to worry about it and will it replace everything in HPC is no.
No. More comments?
So I'll plus one, basically, everything he said. I would phrase it slightly different. You won't miss it if it becomes important, as he said. You don't have to worry about it right now, but it is a sort of keep an eye on this space kind of thing. It's not going to show up next year. The technology is very immature at this point. And as an eternal optimist, I'm going to say all these negative things about it, but I'm trying to build one of these things, okay, and make it actually a practically useful system. Right now, I argue that if you don't have a quantum physicist on your team, you can't use one of these things, because you have to know so much of the detail, and the abstractions that we need just don't exist. We also don't know how to actually integrate one into a larger system, and really the way you would do that is they would follow a path very similar to what GPUs have done. They would be an accelerator in a classical, well, we now use the term classical, or a traditional CPU-GPU cluster. And again, if successful, it'll get integrated more tightly into future systems. But we're looking another 10 years out. Sorry, you've been at it 10 years, but it's going to be another 10 years at least before we see something really more generally useful. So it's out on the horizon. You can take a look at it periodically. If you have a passion and interest in it, I think it is worthwhile, because we do need some, some crazies like us out there trying to make it work anyway, even if we're not really sure it will. I think that's the bottom line, is that we don't really know the answer as to whether they're going to be practically useful or not. But there are folks out there trying various things, and we'll see how that goes.
You can speak for a little bit. We'll go maybe a few more minutes, and then if there's anybody in the audience who has really strong feelings about this, you can speak up too. Go ahead, Estella.
Yeah, well, the only thing to complement what John just said is that you can, if you are really interested in trying these things out, you don't need to think about taking your whole application onto this new system at once. You can think about, is there a part of my code that naturally could profit from a quantum computer? So do you have an optimization? You have to find the absolute maximum, the absolute minimum in a very multidimensional field of possibilities. You can think about porting this kind of kernel to a quantum computer and leave all the rest onto your HPC system. But again, if you are really interested, if you think that there is potential for this particular part of your code, it's something you could enjoy looking into. I wouldn't recommend to take the whole 10,000s of lines of CFD code or whatever and think, let's put all that stuff into a quantum computer. Yeah.
Yeah.
And yeah, I would agree that in general sense, it's a no. But if you are working in some specific fields that potentially can use quantum computers in future, I think it's just interesting, because it's, but just by our curiosity to have a look at how different algorithms map to quantum computers. So the examples might be, I don't know, quantum chemistry or machine learning, right? Like it's like putting two buzzwords in one, quantum machine learning, but it actually exists, and it's an interesting interesting concept, and just to look at how the algorithms map to those systems.
Does anybody out there want to make a comment or have a question? Go ahead.
To the expert, I guess, on the panel. I've heard the analogy is CPUs and GPUs in classical computing is like a car on land for the algorithm space you apply. And quantum computing is like a submarine where you could explore the ocean of, certain problems that you you need a submarine to explore inside, Do you agree with that or disagree?
Yeah, it's certainly a very interesting picture. But you can make this kind of analogy, I think, analogy for any kind of accelerator, right? And I certainly do not believe that quantum computing is superior because of some quantum magic thing. It's perfectly okay to just see it as a black box, as an accelerator that can solve some certain problems better if it really worked according to the model that we have of quantum computing. Which many of the current systems don't do, by the way. But yeah, quantum, the word suggests, and your analogy also suggests, that it is fundamentally capable of doing something much more, like exponentially larger than our classical systems. But these pictures, they rely on a theoretical, on a model, on a quantum physics model that we have of the world. And as a matter of fact, all models are wrong, right? Okay, the quote continues, some are useful, that's true. But it's very easy with this field to get caught up in this, say, magic thing. And it's much more realistic to just view it as a kind of accelerator that can do a specific set of problems well, if it was working properly. But for most of the other problems right now, there is no reason to believe that it will bring much. Maybe it's capable of solving these, targeting these applications, but it won't actually bring much in terms of complexity or in terms of wall clock time or anything like that. So these analogies are always sort of, yeah, they are nice, but they can give the wrong picture of the world.
Okay, thanks. All right, I think unless anyone really wants to say something else, I want to move on a little bit. So we talked about quantum computers, and I think the next highest question was about programming languages. And I'm going to make this a little bit different. I'm going to throw something else in there. So is there a future for C, C++, Fortran? And I'm going to mix in MPI and OpenMP to save time. And I'm going to put a spin on this. Why do I need to learn it when ChatGPT will write it for me?
What the heck? But I want to bump it up a level about the way technologies are used in a community like this. So if there's a couple of things you need to avoid if you want a technology to be successful. And ultimately, the bottom line is if there is not a smooth transition path from where you are to that new technology, it will not get adopted. So if poor Eric over here was told, you know, GROMACS is great, but suddenly there are no CPUs anymore and all you have is quantum processing units, he probably would not know what to do at that point. Another thing to keep in mind is we think about the academic community a lot, and usually it's about the ease of use and the transition path. But another huge driver for these things is what goes on in industry. And industry has a whole stack of applications that are ancient, and they are scared to death to change them because they were written 20 years ago by people who are either gone or dead, and they don't know how they work. And what's most important to them is that they continue to get the same answer because there are huge liabilities potentially involved in that. So you've got a lot of pressure to make sure that there is a smooth transition path from one technology to the next. And if you don't provide that, it's probably not going to be successful. But that means that older technologies have a very long life as new technologies come in. This is why we have seen Fortran around for so many years. It's why MPI has been so successful for so long, is that it provides for that. And if you can't do that, because you're spending a lot of time here figuring out how to use these technologies, that's not getting your science done, right? You're going to use them as a tool, but by and large, a researcher doesn't want to have to keep learning tools and how to use tools. They just want to use them to get the science done and focus on the science. And the more time you have to spend on the tools that you use, the less likely you're going to be wanting to spend time on that.
Okay.
So,
well,
so the answer is yes, there is a future for Fortran. It may be a very, 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 very slow decline, but there are many forces that will prevent it from being pushed out.
okay, Estella, I'll let you make a comment, then I want to ask the audience a question. Go ahead.
Yeah, so an addition to this is that I think it's important to have an understanding of things like Fortran, C, or C++, even if you end up programming Python, because those other programming languages allow you also to go much closer to get the performance of the system and to understand where performance comes from. So I think it's necessary to have a knowledge of how to map a given problem onto the hardware properly so that there is the potential for getting performance. I don't believe that ChatGPT will write you perfect code out of the magic box. And even if it does, you still need to have the judgment and the knowledge to assess whether what this tool has thrown out at you is correct or not. So basically, ChatGPT will not help you to shut down your brain, so you still need to think about, is this what I actually wanted to get? So does this give the solution that I was asking for, or does it give me something that is actually just wrong? So it's giving me the right result, it's giving me the wrong result. It can help you to get into the first step of having like a skeleton of a code or something like that. But you need to have enough knowledge of what is how does it work internally? How does this code should actually look like to understand if there are mistakes on whatever you get out of the tool. So that's why I think it's still useful to have a knowledge of C or Fortran or something of other languages that we're working much closer to the hardware.
Okay, go ahead.
Yeah, I just wanted to plus this and say that in Eric's talk it was the importance of code review. If you use those tools, you will be doing the review of whoever creates the code. If it's AI, you must review it as well. So you must have basic knowledge about the programming languages you use.
And so what I wanted to ask was just, who here has used ChatGPT to create a piece of code? And then have you run it and did it work? Yeah. Okay, so it is a great tool. It is a wonderful tool, but you really need to get some understanding. That's why we think these courses on MPI and OpenMP are so important. Okay, so go ahead.
One other way to look at ChatGPT with respect to this is think of ChatGPT as a junior programmer. It can generate some initial code. It doesn't always write. It usually isn't very performant, but it saves you a lot of time in getting going. So there is an advantage to using it.
So it's like a new grad student. All right. Do you have any comments? Is there anything you want to say? Does anybody want to advocate for the special ML tool that can write all their programs? You can speak up here. No? Okay. Now I'm going to ask go ahead. I want interaction.
Related to ChatGPT though, I wanted to ask, do you see maybe C is old and has some technical problems, but it's simple, It has it's not memory safe and things. And so C++ is an evolution of it, but it's like a monster language that has so many things. Do you see the potential for a new language that could be more modern in some way and replace C++?
So I'll say that every few years there seems to be a hot new language that it's going to replace sort of C, C++, or Fortran. Right, Julia's the most recent one. Apparently easy to program in parallel for it. They need to get sort of wide, broad adoption before they take off. And so it's hard, even if you develop the best new language on the planet. Does anyone have any comments?
No, I think you are saying exactly what I was thinking. So it's also related to your comment from before. It's all the legacy code we had out there that will need to be transported to if you have the perfect new language that solves all problems, even in that case, it would take decades for this to be adopted. So I personally, especially on the programming environment side and on whatever faces to the users, I'm much more convinced that an evolutionary approach is more successful than a revolutionary one, because it is making easier to adapt all these tons of code that are out there. So new extensions to C++, new frameworks or whatever, okay, but completely throwing out it and going something new, I don't believe this will happen.
I'd say C++ is the best example of that, the way it's evolved over the years and the extensions that have become part of the standard, right? So.
Yeah, I would also add, I think Python is actually interesting because 10 years ago, there was first discussion on how we'll support Python and HPC. Now, there are a lot of researchers that are using it actively on the systems. Underneath, they are using C, C++ or Fortran libraries, but we have learned how to support those languages. And I think Python had a pretty good, it's
actually I think I agree with you. I think if Python can fix some of their I/O issues, they have the most potential, because that seems to be what kills us at our center.
But what we are seeing now is that Rust has maybe it's just an Australian thing, but I've seen a couple of researchers that are requiring us to support Rust on HPC, and other centers are also aware of that and are looking actually at how you can support Rust. So from my perspective, this might be an interesting